everybody, welcome to week 14, day 1. And so we're looking at one of the reports. The name is hidden, so don't worry. Insert a value by going to its address, assigning it if open, if not linearly, find next available chaining at a BST, remove marks the bucket as deleted, linearly chaining deleted in the BST. Search checks the first address, then linearly searches the other addresses. If it's not there, chaining it searches the BST on that address. Change called search for a field value exists. If so, it removes it, then inserts. Yeah, okay. So that's you know how I did it as well. I didn't write a change function. I just said search. If it's in there, delete it, insert the new one. Easy. Figure 1 highlights the slight differences in performance between linear and chaining. For the rest, marginal advantage of linear and lower load is not visible. All right, so let's take a look. Okay. Yep, that's about right. Insert. I don't know. Oh, I see. The scale on this is so off the charts we can't actually see the difference down here. But this looks about right. In general, linear probing is actually faster than chaining, but chaining's got a better cap on its runtime. It caps at it in log n, whereas linear probing turns into order n squared to insert n elements. So that's a classic hockey stick graph. Which is why you can do things like, say, if your load ever exceeds half, do a reallocate, something like that, and then you can keep it in the nice performant zone. Alright, so inserting, then searching, linear probing is faster, inserting, then removing, linear probing is faster except in the high end, and again, you have this, see, I would probably graph this on a log-log graph, you know, or logarithmic scale, because we can't actually see who's faster in this zone because the performance of linear probing is so bad. On the high end, it's smashing everything into zero. So I'd probably change this to be a logarithmic y-axis, and then you can actually see which one's better throughout a wider range. Okay, so it looks like the winner here is linear probing. All right, well, one question I have is, the implementation. So let's take a look at this. Okay, so the implementation, linear probing, hash, public hash, enum class status, that's all nice stuff. All right. Yeah, okay. So he added a runaway loop detector. This is actually good practice in general. If you've got a loop, you're not sure that it will actually run forever or not, you know, it's a good idea to add a runaway loop detector. And so what you do is like what he does here, make an int for a counter, and then every time you go one step through the loop, you increment the counter, and if it exceeds some runaway loop threshold, then you stop it. You stop it from doing it. So what happens if it... Yeah, I don't think this handles being full correctly, because it'll stop the loop, right? I see, so it just doesn't insert anything. So we come back to the original spot, not inserted. Okay, that's fine. Yeah, what I would do is rather than this exactly, I would say, you know, if counter is greater than or equal to size, here. You guys got experience working with studs. Do you guys like having to write STDs everywhere? Is that fun? Is that exciting? I would personally do it this way. Just it's a little bit cleaner. So if it doesn't, if you have an infinite loop, then it just returns. Right now, this code, yeah, it finishes the while loop and then it moves on, but everywhere after that, you have to like check to make sure that it was actually legitimate, the spot that you ended up with is legitimate, I would just bail early. That's my take on it. Okay, so for remove size to address, okay. So this is linear probing, cool. So we take the number to be, right. So yeah, one objection that I have here is that he didn't use the hash function. So this hash table that we made, sure, for the assignment, we're only using it for integers, and so this code will work. But if we ever try making this a string, a hash table of strings, then it won't work because you cannot modulus a string, right? And so the hash function will hash any primitive data type, and anybody who wants to put their stuff into a hash table with their own data type, they will overload the hash function for it. So, you know, this is the more proper way of going about it, and it'll work with integers or strings or floats or whatever. You can hash anything using this approach here. This will work for the assignment, so you know, whatever. I'm not gonna knock points off on it. Looking at the grades here. Interesting mix of people being able to get it to work and being able to get it to partly work. It looks like if you did absolutely nothing on it, you passed 5 test cases, which fair enough. Okay. So yeah, all right. So we take the data, modulus it by the size, we get a bucket that we're going to write into. If that spot is filled and the counter is less than size, okay, yeah, all right. If we ever get to an open spot, yeah, I don't think this will work. Let's see. I think this is a bug in it. Let me see. So we're doing lazy deletion. Lazy deletion means that when you delete something, you just mark it as deleted and call it a day. And so this is correct. So like, let's say we hash the number 5, it goes to bucket 5. Counter is less than the runaway loop counter is irrelevant here. If the data matches the data we're trying to delete the number 5, cool. Then we mark it as deleted and bail. Now, what if we inserted 16? 16 also hashes to 5, it goes to the next slot. And then we try deleting 16. This won't find it. The reason why it won't find it is it comes to bucket 5. 16 modulus 11 is 5, right? It comes to bucket 5. The status is not filled. It quits. It will not delete the number 16. So this indicates to me I need a new test case, right? I need a new test case. I also want to find out which test cases people who have not done the assignment are passing. Right. Change those as well. So I will make a note about that. And add test case for insert. So if we insert 5, insert 16, delete 5, search for 16. And then remove test cases people are passing via doing no work. Then I'll update those test cases. All right. Bridges survey didn't let me submit. Kept saying empty field. I don't know. Even after you typed done. Empty field. Are you talking about on Canvas or on the survey itself?
Yeah. So on Canvas, I saw some screenshots of people would type in done, and then you hit submit, and then it would give like a Canvas warning, like saying like the field is empty, like they didn't type anything at all.
This is on PC or what?
It's probably just on Chrome or something.
You didn't have to delete it from the data vector? Nah, you don't even have to touch the data vector at all. So the trouble here is this needs to keep going while it's filled or deleted. So the proper thing here is or status.at address equals status deleted. Right. So as long as you're looking at things that exist or have been deleted, you have to keep going to the right. Once you hit an open spot, then you can be like, yeah, I couldn't find it. So, yeah, that's the downside to lazy deletion, is that there's a zombie thing still in there and you have to just skip over it. This code is not going to skip over a deleted item, and so this code here is incorrect. Okay, search. All right. So, again, the hashing will only work on integer types. The t's must be integral types. All right, if debug, I don't care about that. All right. So here is the actual code. While the, okay, so we hashed, like, let's say we are searching to see if 16 is in the hash table. 16 modulus 11 is 5, we go to bucket 5. If that bucket is not equal to open, then, and we have a match, and it has not been deleted, then we set return value to be true, and we move to the right. Ooh, no, oh no, this is an order in operation when it doesn't need to be. Yeah, so basically, even after you find it, it's going to keep going one to the right, one to the right, one to the right, one to the right, one to the right. So even if you find the right person, it will, in theory, hunt through the entire array after it found it. Rather than doing this, this needs to be return true, like that. You stop the loop immediately if you find it. Don't keep going through the entire array. If you have found the number you're looking for. If you found 16, don't check 17 and 18 and 19 and 20. Don't keep going through the hash table. There's no reason for that. Yeah. Okay. All right. So it needs a break. Yeah. You don't. I mean, you don't need a break. It just needs to return. Yeah. Once you find it, just return true. And then after you get through the whole thing, if you didn't find it, after searching through every spot you can search, just return false. You don't need a return value. Yeah, that's an accidental order in. Yeah, might be why your when it gets full, right? It jumps to the right spot, it finds it, and then it keeps going through the entire thing. So if you do a million searches, you're doing a million times a million operations instead of a million operations, and that's why your running time spiked when it's full. For other cases, it'll eventually hit a spot that's open and it'll terminate, but when the thing is mostly full, it explodes in running time. It'll explode in running time, worse than it should explode. Okay, so change. Yeah, change should be literally 3 lines of code. If the search, is it in there? If it's not, return. If it is in there, then delete the old one and insert the new one. There's no reason to do this whole thing. Okay, so chaining hash should be fairly small. So we have a vector of binary search trees of int, and we have a status vector, which we completely do not need at all. Like that. Okay. Because the status vector is only for linear probing. For linear probing, you have to track the state of each of the buckets, right? Is there a value in there? Is it open, or has it been lazy deleted? Okay, so if we're going to insert into this, then we did good hash. You find the right bucket. So if we're going to insert 16, we jump to bucket 11, and if the data at address is empty, insert. Otherwise, see if it's in there. Otherwise, insert. No, you don't. No. You don't need to do all this. Done. Okay, get the address for remove if it's empty, or if there's no count, it's empty, not deleted. There, it's in there. All right. Return account. And there you go. Do we care about dupes and chain hashing? The set class does not allow dupes. So if you insert something and there's a duplicate in there, it'll simply ignore it. If you try erasing and it's not in there, it ignores it. So each one of these lines is one line of code. And then for change, yeah, this is going to be buggy. Okay, no, he is searching. Okay, he is searching. So that is correct. Yeah, this is what the other search should, or the other change should look like as well. Search to see if it's in there. If it's not in there, just bail. It's on the table. Otherwise, address isn't used at all. Make. This is why we turn on all warnings. Unused variables all over the place, right? There's a lot of problems with this code. He does have O3 turned on though, so that's good. Yeah, this isn't used. Delete. And then there are some issues up here with mixing signed and unsigned integers, which is always dangerous because a signed integer turns into an unsigned integer, so -1 turns into max int. So always be careful, make sure you use size t properly, and yeah, so you're comparing a signed and an unsigned integer here. In this case, it should be fine, but in reality, counter should be a size t also. Okay. That way, you're not mixing comparisons of signed and unsigned integers, which is a foot gun, a very subtle foot gun. Because if counter ever became -1, and you compared it against an unsigned integer, -1 becomes max int, which may or may not be correct or what you wanted. Warning, suggest parentheses, line 67. Yeah, okay. Yeah, you actually do need parentheses here. Order of operations. That's actually an order of operations issue right there. So while it's either full or deleted, and the counter is less than or equal to size, and has higher priority than or, and so it would do the and on the right two side, and then or that with the left hand side, and so that could feasibly. So the runaway loop counter, I think, won't work in that case, because as long as every spot is filled, then the runaway loop counter won't activate, because it's the first guy, if it's filled or, which is true, or it's deleted and the counter is less than size. And so that actually will, that bug with the parentheses there would actually cause an infinite loop in the code. So always turn on warnings and always pay attention to the warnings. Comparison, counter, size, 126 or 117 maybe, auto, address, old data. Size, yeah, that should be.
Because counter's an int.
Yeah, but also address should be a size t also. Because this is a bucket. You can't have a negative bucket. Right. And so if they tried inserting a negative number, then your code would crash. Okay, let's see if we are passing the input tester still. Good, passed all the test cases, but like I said, there was a bug in there, so I'm gonna have to update the test cases. Chain hashing is way slower than linear. All right, let's take a look. Become Benninghoven. Let's see. Hash table mark 1, hash table OG. So the first question I have is, do you have the optimizer turned on? And the answer is, you only have O2 turned on. I would turn that up to O3. Oops. O3. Always, if you're going to be benchmarking stuff, you got to have the optimizer turned on. You will have vastly slower code with O2 than O3. All right, vim hash.h. Pushback. Oh, you're using a list. Yeah, that'll do you. The sets give better performance than lists, right? Pushback, remove. Yeah, and so you're just like looping over the entire. That's an order in operation there, right? So if you have everybody hashed into one bucket, then it's going to be an order in operation to search it every time. Another thing I would do here, and this applies to the previous as well, which if you ever find yourself copying and pasting the same code over and over again like that, then make it a function, right? And this function does not need to be public, because main doesn't need to know how we hash things, but so we can make a private function, and we'll call this private function ha, and it will take in a key called data, and it will just do this. So we will return that. And so we just, you guys see that? Like, if you have copy pasted code over and over again, there actually could be a very subtle bug in here, which is if you change your hash function in one place, you don't change it in the other, then the search isn't going to be able to find what you inserted, because they're going to different buckets, right? And so what we will do is, instead of copy pasting that code, we'll just say ha data. So it's going to hash the data like that. Yeah. A lot more compact. One line insert, one line remove. Search should be one line as well. Yeah, so basically did you guys see that I made a function called ha? It takes a int, a t, but it's going to be an int. And so whatever data we take, we pass it to the hash function here, and then it calls hash on it. And that just keeps me from having to copy and paste the same line over and over again. So does list have a search function? Count, clear, place, find?
Probably have to use the standard find.
It doesn't have a member search. It's interesting. I very rarely use lists. Very rarely.
Yeah.
No count.
Especially because I just calculated that for a 999K, it's obviously 999,000 operations worst case for search. For a BST, it's 20 operations worst case, which is a pretty big margin.
Yeah. The BST version has a much lower bad side to it. All right, so yeah, we'd have to use find, and so if it returns end, then we return. Let's see, could we one line that? We probably could. and it returns end. Okay. Alright. Let's see if we can one-line this. It's an algorithm. It's an algorithm. Yeah, okay. So return find from table.begin to table.end. So we're going to search the whole thing looking for data not equal to table.end. Okay. So find is going to search through the entire linked list looking for data. If it is found, it returns an iterator pointing at the place that was found. If it does not find anything, then it returns table.end. And so if the pointer we get out of it, the iterator we get out of it, is not equal to the end, that means we found it. So we return true, because the iterator we got was not the end. If, however, we got the end, then this is false, because end is, the same as end, so not equals is false, and so it returns false. And we can't do this, actually. We have to say table.at, right? Data. That's ridiculous. Okay.
Missing a closing parentheses before the dot end.
Yeah, and this is why I really wish that you could just pass one thing, because you have to repeat it over and over again. Ranges will make this better, but it's fairly verbose. That's a fairly gnarly one-liner right there. So
same for the begin also.
Table is a vector, so we jump to the bucket in the vector based on the hash. That is wrong right there. Yeah. Table.add. Yeah, and so table.add, it jumps to that bucket, the end pointer to that linked list. It's not equal to table.add ha data, and I'm missing one more, aren't I? Yeah. There, table.add ha data, and so yeah, that's a fairly gnarly one-liner. I probably would break it up at that point. That should work. Make new data was not declared. Where is new data? There we go. All tests passed, and code's a lot more compact now, So. I would use a set. The code for the set, like you saw on the other code, is you call count. It tells you how many things are in it. It's kind of annoying to me that the list class doesn't have a count option. I don't know. But there you go. So that's the one-liner for a linked list, which is a lot more verbose. Like I said, I don't use linked lists very often. It's an order. This is an order in operation, whereas with a binary search tree, it's login. Wonder if the timing got better on bench. Yeah, Benninghoven, if you could re-bench something, let me know if the speed got better. Okay. Can we talk about how the deleted status is useless? What do you mean? Wait, what do you mean the deleted status is useless? You only need open and filled? For what? For linear probing? No, you have to have deleted. I mean, you can do a cleanup operation, right? But yeah. Here, let me sketch it out. There are implementations that don't do lazy deletion, and that's fine. There are ways of doing it without it, but we're doing lazy deletion for this one because it is the least code, and I typically teach the simplest ways possible. So let's say we got a hash table, and over here we got bucket 5, we got bucket 6, and our size is 11. We hash the number 5 modulus 11 is 5. So we're going to write the number 5 into 5. And then we've got a status array down here, and this is set to be filled. All the other ones are set to be open. We then hash in the number 16. 16 modulus 11 is also 5. Uh-oh, we got a collision. 16 tries coming in here. It's got a collision. And we know because it's filled, we need to go to the next. We don't have a match, and it's filled. So we need to go to the next one here. And we need to, oh, it's open. Okay, write 16 in here. Now, let's erase 5. If we erase 5, then this needs to be set to deleted.
Don't forget to set 16 to filled also.
Yeah. So, if we set this to be open and not deleted, if we search for 16 modulus 11 is 5. It comes here, says the bucket's open, return true. It will not find the 16.
But I just said if it's just not filled.
What does that mean?
In my if statement, I basically said if it's not filled, then you can put it there. Right?
Something's either there or not there. Yeah, you need to mark this as deleted so that you know there's something used to be there because 16 is not in the right place.
Oh, I see. Yeah. Okay, you have a good point.
And so what you could do...
I shouldn't be passing all the test cases either.
So what you could do is, come up with some test scenarios and I'll edit the input test. What you could do is when you delete 5, when you delete 5, you could look at the people to the right and rehash them until you find an open bucket. And that turns your delete into an order and delete. Whereas lazy deletion, you just mark it as deleted.
Yeah, I'm going to try running it on my debug again and see if that actually happens or if I did something different. Yeah,
but this is a bug that the first student's code has, where if you insert 2 to the same spot and then delete the first one, it won't find the second one. So I definitely am going to make a test case for that. And I will rerun it. So the good news for you people that are not passing some of the test cases, I'm going to rerun the grades. So those of you that have the bug, get it fixed ASAP. If you have this problem where if you insert 5 and 16, let me just verify that would be a case of the first student here. See, hash table, a linear mode, insert 5, insert 16. What is it, remove or delete?
I think it's delete. Or, oh, never mind, it's remove. Okay.
Search 5. Good. Search 16. In table. So how is that possible? Did I fix that on this code already? I think I did, didn't I? Yeah. So the search is finding it, but if we do this, let's see here. Yeah, I fixed that, didn't I? Yeah. Right.
Yep, you're right. It didn't work with my code.
Yeah. 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 So, and also if you mark it as open, you can possibly have a double insert. Like if you came back in here and then inserted 16 again, 16 would jump to here. Oh, the spot's available. And now you've got 2 copies in here. You see that? if you mark that as open, then if you insert 16 again, you will have two 16s, and if you remove it, so I need to make a test case for that as well. Add test case for insert 5, insert 16, delete 5, insert 16, remove 16. Let's see how that works. Insert 16. Insert 16, remove 16, search 16. Yeah. So if I insert this, then that would be set to be filled. And then I erase it. And then it'll be set back to open or deleted, you know. And then if I search for it, it'll find this guy, which would be a bug. You're not allowed to do a double. Duplicates are supposed to be deleted, right? Or ignored. Okay, so that is the code for hash tables. Like I said, the coding for that is not very lengthy. It's not. You have to have a firm grasp of what's happening conceptually with it, and then you need to have the coding skills to translate the concept into code, and then you need to have the debugging skills to test it and make sure that it is working properly, and not just rely upon my input tester to test for you. Sometimes there's a test case that goes missing. So those are the three skills, right? Understanding the concept, be able to translate into code, and then debug it and make sure the thing's actually working correctly. The first student had a lot of debugging information printing out, which is a good thing. Okay. Server's going to get an upgrade soon. What do you mean the server's going to get an upgrade soon? We're getting an upgrade? It's news to me. Are you talking about the new server? We are going to get a new server, yes. So this machine here will go back to being my own personal Linux box that I use for development. And the school that we just had a meeting on a couple days ago with the district office, and they are on board. It looks like they're going to be cool with us having a Unix box running on their network, because it's going to be completely isolated from the network. You will not be able to ping any other hosts within State Center Community College District, which is a good thing. All you'll be able to do is get out, and it'll only allow incoming connections, not outgoing connections. The only outgoing connections allowed will be to like GitHub. I don't know, but yeah. So, but it's a beefy server. It's a beefy server that was donated by Courtney Choate, who's one of our math instructors. Her husband donated it to the school. I think she actually asked me if I wanted it. I don't have any need for a rack-mounted server, but I was like, the department could use it, So, how beefy we talking? 180 gigs of RAM, something like that. We just upgraded it to like, I don't know how many terabytes of hard drive space. We got like 10 terabyte hard drives in there. We have some ridiculous specs on the thing now. 20 cores, 24 cores. I don't know. It's pretty good. I mean, it's not top of the line because they were getting rid of it because they didn't want it anymore. But it's got, something like 20 cores in it and 180 gigs of RAM, and yeah. I will take that for free. And Nico, who's my boy, he's been working on it, getting it ready, and we'll actually be running multiple virtualized servers on it. So Lawton will have his server on it. I will have my server on it. They won't interact with each other. They're held in separate, virtualized containers basically, and yeah, it'll be pretty cool. So that should be. We have a deadline of that for May 9th or something like that. Yeah. So we will do one more benchmarking assignment before the end of the year. Okay. So let us talk about new stuff. Hash tables in general. Yeah. Yeah. Really, really useful stuff. Really useful stuff. Binary search trees, useful. Hash tables, very useful. Vectors and hash tables are typically the two most common data structures that I use. So unordered map in the STD, in the STL. Okay. How long does it take to set up a server like that? It doesn't take too long. The annoying thing about setting up a new server is just remembering what packages I have installed here. And like I have different shell scripts, and so I've got to kind of copy those over. I've got like the input tester. That's not part of Unix. That's just my thing, and the auto grader and all those tools I have to kind of migrate over and test and make sure they work. Make sure the permissions are set up right. So it's probably, I don't know. Like whenever Nico says it's ready and I can get in there and set it up, it'd probably be 3 or 4 hours of effort, something like that. And then when students try like running tmux or something, they're like, tmux isn't installed. I'm like, oh yeah, okay. And then I'll install tmux for them. And so if you guys ever have a package, by the way, on Ubuntu, which is what we're using here, this is a Ubuntu server, and Ubuntu server is fine. Some people talk smack about Ubuntu server. I don't know why. Like, I like having distributions that have a lot of support. You know, like if everybody uses it, yeah, I will follow the crowd and jump on the bandwagon simply because it'll be easier for me to find packages made for Ubuntu than it will be for some obscure Unix distribution that nobody's heard of. So, okay. Any word on the Unix networking class? Yeah, nothing is happening on that until we're back in person. Like, there's no, absolutely nothing is happening at the sort of higher levels except for figuring out this coronavirus and all that kind of stuff. Yeah. So, you set up the Raspberry Pi server in 15 minutes. Yeah, it's if you're just going to do a stock install, it's fine. But like, which input tester, right? That's in user bin, and which compile, and so I've got different tools installed in different places, and I kind of just got to SCP them all over and make sure they're world executable and owned by me, and it's just kind of, it just takes a little bit of time. It's not hard. If you're going to set up like a web server, then you have to configure your httpd.conf file, and I've got to get fail2ban set up. So fail2ban is the tool that if you try logging in on the server and you type in the bad password, it blocks you for 15 minutes. In this 45 or 26, you learn this. I normally teach how to set up a Unix server in 45. The school has very graciously bought class sets of Raspberry Pis. So I've got a Raspberry Pi here, right? In fact, right there is the server for 45. It looks like this. I've got a lot. I own a lot of these. Probably a little bit less than 10 of these that I own. Just mine personally. And then the school has bought 80 or so Raspberry Pis for students. And so when you take 45 with me, normally in non-pandemic years, you would be given one of these and a bunch of wires and sensors and stuff like that. And you will have to set up a Unix server on this using Ubuntu, GNU Linux, GNU Plus Linux, Ubuntu Raspbian it's called. And you learn how to administer a Linux box. Right? It's got Ethernet, plug it into your router, set up pinholes through your firewall so that people can SSH in from remotely, but you better change that default SSH password or you're going to get the hacks. And yeah, go through all that. Got an HDMI out here, so you can plug it into your monitor. 4 USB cables, so you can plug in your keyboard and mouse. SD card right here. So I got a 30. What is that? How big is that? Stuck in there. Oh, whatever. I got an SD card in there, and this is a Pi 3. Yeah. So you learn how to set up these things. It's a fun class, and we do projects. So you hook up sensors and wires and build physical stuff that you program on the Raspberry Pi to control motors and things like that. So students made pinball machines and autonomous party boats. Like they got this giant styrofoam boat and put propellers on it basically, and ultrasound sensors on the front, and so they tossed it onto their lake, and they played like party music, and they had like Barbies and stuff on it, and the thing would literally go around the pool, and it had flashing lights. It was like this cool, this big thing, and it was playing music that had speakers on it, and it would play party music. And when it got close to the wall of the pool, the ultrasound sensors, which are like bats echolocation, they're like, oh, there's a wall coming up, and then the thing would steer around it, and so it's like a Roomba going around your pool just playing party music, and it was pretty damn cool. Probably a day or two's worth of work to do that, if that. Pi-hole Pi-holes are really useful. Yeah. Yep. So, would you be teaching in your next 45 class during pandemic? No. If the pandemic is still going on next spring, no. But the way things are looking, the feeling I'm getting is that we're going to be back in person. 60% chance we're going to be back in person in the fall, and probably 90 something % chance in the spring, unless something goes horribly wrong. The South African variant apparently is capable of bypassing the Pfizer vaccine, so yay. So we'll see. Okay, so let's talk Heaps. All right. So talked a little bit about Heaps last time. Let's keep this up. Talk about Heaps. You guys should have a link to the notebook. I guess not. I guess you don't have a link here. Let's share this. Really specify can view, copy link. No, just anyone with link. Let's see here. Anyone with a link. Anyone with link can view. Okay, so I'm going to post onto Discord a link to the OneNote, so you guys can look at this whenever you want. Emily, if you want to pin that, here, I'll just make a note. This is the OneNote. Okay, so all these notes that I make, they're publicly available, so you can look at them, marvel at my beautiful handwriting whenever you want. Okay, so let's talk Heaps. Heaps. Okay. So by default, a heap is a binary tree. Binart. A heap is a binary tree. It is not a binary search tree. Is not a binary search tree. Right? So when you start off, what should the root of the tree be pointing to? Pointers. This is the semester with which you should begin getting proficient with pointers. Pointers are useful. Like you saw with the inheritance thing. There's things you can do with pointers you can't do any other way. Min or max. What should root be pointing to on an empty tree? If we have no elements on the heap yet, what should it be pointing to? Null. Right? So by default, root is pointing to null. 0. Okay. 0. All right. So let's insert. Do you guys want to do a min heap or a max heap? A max heap has the biggest number on top, and min heap has the smallest number on top. What do you guys feel like? Min heap or max heap? Min heap. All right, cool. All right, so let's come in and do an insert operation. Let's insert the number. Actually, here's a good example. All right. Let's say the start of your program. Let's say the start of your program is time 0. And we are going to, we're making a video game. This is actually a common optimization. We're making a video game that has thousands or maybe millions of objects in it, and these objects can all think. In other words, they can say, in 3 seconds, wake up, see if there's any players around me, and if there's not, go back to sleep for another 3 seconds. If there are people, then engage search and kill mode or something like that. Okay, so let's say that we, or you prime a grenade, you throw the grenade. The grenade will move through the world, and in 3 seconds, the grenade will explode. So in 3 seconds, call this function. In 3 seconds, call a function that will cause the grenade to explode. So if we were to insert, if the time currently is 0, and we were to insert 3, what should this look like here? And so we're going to be, we're going to have like a struct. What we're going to be inserting is going to be like a struct containing like a time. It's going to contain a time and like a function of some sort. I don't know if you can read that, but we're gonna have a heap that is going to be sorted by time, and then it's also going to have a function. There's 2 things in here, the time and a function. And so what happens is that when that time rolls around, like if the current time is 10, and I say in 3 seconds, call this function to explode the grenade, then we would insert 13, because current time plus 3 is 13. And we insert it into the heap. And when the time comes, it will call that function and pop the thing off the heap. And you'll see why this is cool in just 1 second. So if we were to insert the number 3, what is the tree going to look like? Don't worry about the function for now. We're just going to be sorting it based on the time. In order to sort something, what operator needs to be defined? What operator needs to be defined to sort something, to compare? Which one? Very good. Yeah, operator less than. Okay. Operator less than is used in anything that involves sorting, or having a heap, or having a binary search tree. Anything that involves comparing 2 things, you have to have operator less than defined. For hash tables need operator double equals defined. And so this is used for sort and BSTs and heaps, and double equals is used for hash tables. Okay. So if we insert the number 3 into here, then we are going to new something, and the new thing is going to have time 3. I'm not going to write the functions down, but just be aware that when you do this, when they come off the heap, the engine is going to call that function. It's called a callback. And so this is how timers work. So in video games, timers are really big things. You say, in 10 seconds, do this. In 7 seconds, do this. Every 5 seconds, do this. And what happens is the system that maintains all the timers only needs to look at one thing. Because the server updates 30 times a second, 60 times a second. It does. So you could look at all of the million objects in the world to see if they're ready, because like the current time is 1.5, let's say. And so you could go through all, 9 million of the things to see if they're ready to activate. You could. Or you can just check the top of the heap. Current time is 1.5. The next action that's going to take place in the world is time 3. Don't do anything. Order 1 versus order n. Very, 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 very efficient, right? And then a tenth of a second later, the time is 1.6. Check to see if out of the millions of things in the world that want to activate in the future, see if any of them want to activate. Nope, the smallest value is 3. Return. Okay? It's now time 1.7. Return. 1.8. Return. 1.9, return. You don't have to keep looking at millions and billions of things every frame, which is really, really slow. Instead, all you do is every frame you just check the very top of the heap, and eventually when time 3 rolls around, then it checks the top of the heap. Aha, we have something, right? We have something. And so it's going to pop this guy off the heap using that pop operation I showed you last time. And then the new minimum will bubble up to the top, and it will call whatever function is here. So in 3 seconds, you could do something and say, in 3 seconds, play a sound. Play the red alert sound. So you hit a button, and there's a 3-second delay, and then it goes off. Okay. So when you pop it off, you call whatever function is in this, and then you're done. And then it's time 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, order 1. Nope, we're good, we're good, we're good, we're good, we're good, we're good, we're good. Time 4 rolls around. Yeah, whenever time 4 hits, all you're doing is just checking the top. You don't have to look at the entire heap. Yeah. As the game is progressing, it's going to be adding things, different objects in the world. The player hits throw grenade, it's going to add to the heap. If the current time right now is 3.9, it's going to add to the heap at time 6.9. Nice. Somewhere in here in the heap, it'll add at time 6.9, call this function to cause the grenade to explode. And then maybe you have a monster that, or maybe you set a demolition pack. The demolition pack takes 10 seconds to go off. So you insert at time 13.9. At time 13.9, cause the demolition pack to go. And these things are just going to be somewhere in the heap. It actually doesn't even really matter where they are in the heap. All that matters on a min heap is the next person to go, the next option to go, because 13.9 isn't the next thing to go. 6.9 is not the next thing to go. So they're just down there in the heap somewhere. We don't care. And then time 4 rolls around, right? Time 4 rolls around. All right, pop this guy off. Call whatever function we said to call, and then we see, okay, who's the newest, smallest member? And maybe the newest, smallest member is 6.9. So 6.9 would percolate up to here. And, 13.9 still buried down there somewhere. It doesn't matter. It's not going to come up for a while. And then we go to time 4.1, time 4.2, time 4.3, time 4.4. And we just check the top. It's very, very efficient. If you've got millions of things that are going to activate at some point in the future, a heap is a really fast way of implementing that. Super fast. Okay. How often do IS-50 peeps use data structs? In IS-50A, none. IS-50A is targeted at people that don't know how to program, really. We do block coding, if you've ever done Scratch or something like that, hour of code kind of stuff. The coding in IS-50A is pretty basic. In IS-50B, you have to know C++, basically. If you don't, then, I don't know, like Muya is partnered with somebody who doesn't know C++. And the guy is just kind of like leeching off him. Is he doing anything, Muya? He's really good. Okay, that's fair. Yeah, he is. Okay. I know. I'm not joking either, but yeah, he is actually really good. But yeah, that's how IS-50A and B are set up. IS-50A is just sort of a casual class. We play games, we talk about games, and you implement games using block coding. Block coding looks like this, right? Like you have like a square, and it says like on overlap. And so like maybe you have a door, and the door has like this invisible zone around it, and when the player, how's that the player? Maybe let's try it a little better. It's like when the player walks inside of the zone, then it triggers a callback, and then you just drag out of that and you say print hi. And then when the player walks up, it prints hi to the screen. And you're just like dragging lines around and stuff like that. It's really casual. Every semester I have students drop out because there's a math section. You have to know math to do games. And so like, I don't know, like I'm just like a little bit, I don't know. Like, maybe it's just because I'm a genius professor, but like if you're going to add 1, 2, 3 to, I don't know, 10, 10, 10. The answer is, if you add these two things together, you get 11, 12, 13. Do you guys think you can figure out the secret? The highly advanced mathematics going on here? If you add a vector with 3 numbers to another vector with 3 numbers, I don't know. Is this? I don't know. It's like I present this and students go, I didn't sign up for this. I don't know. I feel like this isn't hard. Like, you just add each of the columns. I don't know, man. It doesn't seem too difficult to me. So, yeah, but you do need to know, or you will learn more particularly, a little bit of math in the class. You'll learn how colors work and things like that. None of it's very difficult, in my opinion. I don't know. But every year there's like a set of students like, oh, I didn't sign up for math. Drop. Okay, so yeah, so that's IS-58. Okay, so heaps, yeah, very useful in a lot of circumstances like that. In Linux, you have something called a task manager. Works basically the same way. Like a program's like, hey, wake me up in 10 seconds, and you're like, all right, and then it just goes onto the heap. Like the task manager will just have the heap. And if you have a lot of people all running at the same time, like your hash tables the day before the assignments due, what happens is you've got 20 people all competing for the CPU. There's only 2 cores on the CPU, right? And so what the task manager will do, the task scheduler will do, is it'll be like, all right, Bender, you get it until 106 and 10 seconds, and then when 106 and 10 seconds rolls around, it swaps you out, pulls the first person off the heap in, runs them for a little while, and puts Bender's code back on the heap to be run in, I don't know, 2 seconds. And then it runs the other person for like half a second. It's actually much smaller than that. But it'll run them for like half a second, and then like, all right, you're out. Come back in 2 seconds later. And it will sit there and sort of round robin process everybody's code that way. And it'll pull whoever's next off the top of the heap, run it for a little bit, and then throw them back on the heap. And it will it's like trying to juggle 20 different balls in the air. And so each ball just gets a little bit of attention at a time, and the rest of the balls are just kept up in the air. And that is called the load on a server. So the load is right here, and that is how many balls are up in the air at once. If you've only got 2 people running programs right now, then they'll just run it, and there's nobody waiting to be run. But if you are trying to run 3 programs, like if 3 people are running their benchmarks at the same time, then what happens is the CPU goes, okay, I've got 2 cores, or the task scheduler says I've got 2 cores, so toss 1 in the air, and then work on these 2, and then throw this guy into the heap and work on these 2, and then throw this guy into the heap and work on these 2, and then 2 more students start running things. Now you've got 3 balls up in the air, and you've got 2 you're working on. You start juggling, and you'll see the load start going up. The load is how many balls are in there, how many tasks are waiting to run. They want to run, they need CPU time, and are just waiting. They're sitting on the heap, basically. And the heap is used to track who gets to run next. And you can do things like nice your program. If you nice your program, if you make your program nice, which is considered good neighborliness, if you're going to be running a program that's going to be running 100% CPU for a week or something like that, it's considered good policy to nice it, to make it nice. And what that means is that rather than coming back in 2 seconds from now, it'll come back in 5 seconds from now. And so your thing is going to be, look, people are starting to run things. Bazookian is running this thing to demonstrate. So if you nice your program, then it goes further down in the heap. It'll wait longer until it runs again. And I can run my program with negative niceness. So if I want, I can negative nice a program. It's actually called nice. Nice. So I can actually run 20. What is it? Nice. What is it? Man. -n. And so I'm running my program with negative niceness. And you saw here, you cannot do negative niceness unless you have root access. If you have root, you can give a program negative niceness. And then you get prioritized over other people. And so if you guys are hammering the server and I want my stuff to run ahead of you in the queue, I can run my thing with up to negative 20 niceness. And then I will just cut to the front of the line. It's like y'all are waiting to get into the club, and like Kanye rolls up. Kanye just goes straight to the front of the line. Negative niceness, boom. Actually, I'm sure he's a nice guy in real life, but that's the idea. A priority queue, that's literally what a priority queue is. It's a queue. A heap is a priority queue. It's the same thing. And so you can think of a heap in terms of like you got a club, you got a bouncer here, and you got, I don't know, the velvet rope here, and you got a bunch of people waiting to get into the club. This is the club. Okay. It's got a bunch of people waiting to get into the club, and each of these people has a default priority of 0, let's say. And then somebody walks up, and they have a priority of 1. Then the bouncer's like, hey, you, come to the front of the line. And so this person will get a walk up here and be at the front of the line. And then Kanye rolls in. He's like, boom, got a priority of 20. Then Kanye gets to go in front of the person with a priority of 1. And so a priority queue, i.e. a heap, they're more or less equivalent concepts. This would be a max heap, right? Whoever has the highest priority gets to go first. We'll keep things in order. It will keep things in order if they have the same priority. But basically, whoever has the highest priority gets to go first. And so that is, the mental model of a priority queue. It's a queue, but if somebody bribes the bouncer for more priority, they get a cut in line. Drake gets plus 20 niceness for being Canadian. Right, so Drake rolls up with his negative 20 priority, and he just waits. Everyone comes in front. Oh, you can go in front of me. Oh, you can go in front of me. Never gets in. What a nice guy. Okay. Did you come up with a name, or is it part of the standard library? Yeah, nice is a Unix. It's part of Unix. And so if you guys are running your batch timing scripts and things like that, maybe I should just add it to the default one, huh? For next year. User bin time. Where would the nice go? Nice 20. Let's see. Time this. No, doesn't like it. Let me make sure. I rarely use nice. Let me look it up. Nice is negative 20 is the highest priority, and 19 is the lowest priority. Okay. Default niceness is, yeah, there we go. There we go. That is not running fast. Does the code work? Maybe the code doesn't work. Maybe that's too nice. I don't know. Just nice it by 1. See if that makes a difference. Copy. Timing script up into hash table dot reference. Before I copy it, I want to diff it. Oh, I don't have one. Okay. Input search. Input search. Calls these things input search. Such a stupid typo. All right. Input search. All right. So 0.35, 0.34. Okay. And so let's run it with niceness of 19. Okay. Not too bad. Not too bad. Not too bad. Yeah, looks about the same. So I'm going to background that and htop it. And you can see here that my program is running with a niceness of 19. Okay, so I might actually just make that part of the shell script so it doesn't hammer the server. And students that are smart enough to learn how to delete the niceness out of it will get their code finishing faster. How about that? Okay. So copy timing script up into hash table. Cancel. Okay. You guys understand niceness? So basically, when you add niceness, it lowers your priority on something. Nice guys finish last, yeah. Or rude guys who think they're nice guys finish last, even more. Okay. So yeah, all right, that's a hash table. That's a heap. All right. And there's something called a treep, which is a combination of a binary search tree and a heap. And so what it does is it assigns a random priority to things that you insert, and that has the effect of randomizing a tree to cause it to be balanced. Kind of cool. You can read about trees. We're not going to use them in this class, but that's in Zybooks. You probably should have read about that already. Yeah, so this is kind of where we left off last week on heaps. Treeps are cool, but yeah, don't worry about them for this. So one of the really nice features about a heap is that every time you insert, it just comes into the next available slot, right? Every time you insert, it comes into the next available slot. Every time you delete, you switch the root with the last person and delete it. And so the trees are always full and complete. There's always no gaps anywhere within a heap, and the only person who might have one kid and not 0 or 2 is the person we're currently inserting into. And so this has the benefit of allowing us to store heaps into an array. So the root is at index 0, the left child is at index 1, the right child is at index 2. There's a little bit of algebra on figuring out who your left kid and your right kid is. So you take your current index, multiply by 2, add 1. So 0 times 2 plus 1 is 1. Your current index times 2 plus 2. 0 times 2 is 0, plus 2 is 2. Okay. So a little bit of algebra. It's not too baffling, I don't think. So that's index 0, index 1, index 2, index 3, index 4, 5, 6, 7, 8, 9, 10. And then you don't need pointers. If everything is in a vector, then you don't need pointers. And so every time you add something to a heap, you just call pushback on the vector, and it grows by 1. And if you were to insert, let's say here, what is this, in max heap? Let's say you were to insert the number, I don't know, 8 or something. Then 8 would go in here, and then you just see if the heap property has been violated. It has. The parent is smaller than the child. And so you turn that 8 into a 6. You turn, oh, there's already an 8 in here somewhere. Yeah, whatever. And so you switch the 6 and the 8. And this index here is 11. And so we know the index of our parent is, you just divide by 2. 11 divided by 2 is 5. Integer division, right? 11 divided by 2 is 5. My parent is at 5. And so you just check to see if the value at your spot is bigger than the parent's position, or the value at your parent's position. And if it is, you switch them. And so you take the 6 here and put it here. Take the 8 here and you put it here. So this turns into an 8. This turns into a 6. And you repeat until you get to the either get to the root or that your parent is bigger than you. So you compare 7 and 8. So you take 5 divided by 2. 5 divided by 2 is 2. Index 2. 7. 7 is smaller than 8, so you switch it. This 7 turns into an 8. This 8 turns into a 7. And then you compare the value here, which is now an 8, with 11. The heap property is satisfied, and we stop. And so this is called bubbling up. Bubble up. And when you delete, you bubble down. So when you delete, you switch the 1 and the 10, or the 1 and the 11. You switch those, delete the last one. This turns into a 1, and then you're like, okay, bubble down. So 10 is bigger than 1, so you switch the 10 and the 1. This turns into a 1, this turns into a 10. 9 is bigger than 1. This turns into a 1, this turns into a 9. 8 is bigger than 1. This turns into an 8. This turns into a 1, and we're done. And that's a heap. If you want to use a heap in the standard library, it is called a priority queue. There's actually two different heaps in the standard library. There's one that is from the SeaWorld days, and don't use it. There's a function called make heap and things like that. Don't use it. Don't use it. Nah. What it does is it takes an array of integers and it puts them in heap order. So the first element is the biggest, and then these two are its kids. So it actually does this. Like you just pass in an array of integers and it puts it in heap order. So that's the root. These are the two kids. So it simulates a tree for you. Array representation is pretty cool, but it has some huge performance benefits as well. This is make heap. So make heap takes an array and it takes a vector of just integers, and then it turns into a heap form, and then after it's done, it is in heap form. So you can see here, this is just an array of integers, and after it's done, the root is in index 0. These two guys are its kids. These two guys are the kid of 5, and this one is the kid of 4. And this would make absolutely no sense to you if you did not understand this. So do you guys see that? So rather than having pointers to the parents and left child and right child and parent pointer and all this stuff, you just save it into an array. And it's always compact. There's never any gaps in it. You don't have to worry about null pointers at all, null pointer dereferences. If you're ever going to insert something, you just call vector.pushback. Boom. You're done. And then you bubble up or bubble down. But if you don't want to do the bubble up and bubble down, there is a std function called make heap. And so make heap turns an array of just integers into heap form. So the biggest element, the root, is at index 0. The root's kids are at 1 and 2, so on and so forth. And then you can call push heap and pop heap. And again, it just takes an array of integers. And pop heap takes the top element off the heap. Right, so or it bubbles it to the bottom, right? So you have to call pop heap, and then that moves the root to the end, and then you call back, or not back, pop back, and that deletes it. So you call pop heap, and it moves the top element to the end, and it updates. It does the bubbling operations for you. The biggest element's now at the end. You print it, and then you call pop back, and the vector shrinks by 1. And so you have to do all this stuff kind of manually. It's kind of a little, yeah. I mean, I don't know. I wouldn't use it. I would use instead priority queue. So, so make heap is like a relic of olden times before we have classes and things like that. So priority queue is the heap data structure. Okay. Am I going to regrade the hash assignment with the new test cases? Yes, I am. So for those of you that didn't do the assignment, I solved it for you. So like do it or something. I don't know. Pass the test cases. And for those of you that didn't do the deleting right, I am going to update those test cases. What was the test case again? Insert 5, insert 16, delete 5, search for 16. To make sure that you're handling the lazy deletion properly. A couple different variants on that. And then I'm going to find the 5 that people are passing without doing any work and get rid of those. So no free points. But, I mean, you saw how easy the set-based version was to implement. It's half the test cases. Like, it's just free points, man. It's just free real estate. All right. Priority queue, priority queue, priority queue. So priority queues have push and pop, right? And top, like just like a queue or a stack, right? It's top instead of front. It's kind of weird. So push adds an element to the priority queue. Pop gets rid of the first thing in the priority queue, and top tells you what the first element in the priority queue is. That's just kind of weird to me because the queue class uses front, but the priority queue uses top. Probably because it's a heap, right? But probably because it's a heap. It's just an interesting. Someone managing a heap. It's just free real estate. And it's another one of these adapter classes. It actually just sits on top of the vector probably. Yeah. So yeah. Push, pop, and top. That's all you need to know about a prio queue. So yeah, it's just we got a couple minutes left. Let's just do a little priority queue action in here. Show you guys what that looks like. Cd then prio queue.cc. Include queue. We'll include queue.h. Anymore. Why are you complaining? Go away. Alright, don't need you. Don't need you. Don't need you. Don't need you. Alright. So while true, int x equals read, please type in an integer to insert into our priority queue. 0 to quit. So we're going to need a priority queue. Priority queue of ints. So we're going to be holding integers, and so the integers are just going to be the priority, and we're going to call this guy prio. And so prio.push x, but if x is 0, then we break. Okay, so the user will type in 10, 20, 30, 0, whatever. When we get 0, it quits. And all the other ones will be added to the priority queue, and then we can say while prio.size. Yeah, okay. While there's elements left in the priority queue, integer x equals prio.top. Get the first element of the priority queue, cout it, and then pop it. So the 3 commands are push, pop, and top. Those are insert, delete, and search, but it's not really search, it just gives you the top element of it. And that's all you need to know about a priority queue. This is a heap. Boom. I guess size. Yeah. So we'll type in 10, and 1, and 30, and 100, and negative 100, and negative 9,000, and positive 9,000, and we hit quit. And you can see, voila, we just sorted the numbers. So what I implemented right there is an algorithm called heap sort. Push everything into a heap, pop them off, it's sorted. That's it. That's it. Okay. So it does a max heap by default. You can pass in a comparison operation, like with sorting and the other things. You can pass in a comparison operation to make it sort least to greatest. Okay. Like that, yeah. Okay. So that is a priority queue. And I'll toss this up for you. Copy Prio queue into slash public. If you guys want to copy that, it is in the public directory. Its name is prio_queue.cc. And that's just a little simple implementation of a priority queue. And or a heap, same thing. Push pop top, that's it. Do you guys see how nice it is? Like, you don't have to write this stuff, you know? Like back in the day, if you wanted a heap, you had to write a heap. And so this class was utterly essential because you had to make all of your data structures yourself. Nowadays, I show you guys how to do it because you have to understand what's going on. But in reality, you're just going to be like, priority queue, add some stuff, pull some stuff off, done. See how small that is? I didn't have to mess with pointers. I didn't have to do the array accesses, any of that stuff. Pretty easy. You guys are living in a charmed time. Computer science is easier than ever. You got address sanitizer. You got standard libraries that are decently okay. Computer science is still hard. The hard thing now is just solving the problems. So I guess I'll give you guys one more day to do the... one more day? I don't know. I can't post this video because I've just literally solved the entire thing for you guys. So I'll just make an announcement on Canvas. You know, I'll regrade this tomorrow. And yeah, and then you'll get your next homework assignment on Wednesday. Okay? So good luck to everyone. And if you haven't done the hash table thing yet, congratulations. Because I found there were holes and gaps in the input files, there will be a reckoning. No, sorry, an extension.
If you saw, I sent that will an input test that will expose.
I saw it. Yeah. Perfect. Yeah, and I'll put that into the test cases. Okay. When will the new input tester be up? I'm going to work on it right now, so it should be up by 2 o'clock or so. Okay. Depends if I eat my sushi first or not. Yeah, probably by about 2 o'clock. All right. Thanks, guys. See you.